students, this is Unit 1, Similarity, Lesson 4.3, Similarity Shortcuts. Make sure you get the date and location, as well as a parent or guardian sign-off. Go ahead and use the concept of similarity in order to solve for x below. Pause the video, do your own work. Welcome back. Let's take a look here. First, you want to match and mirror the sides. So we're going to go short side to short side, medium side to medium side, long side to long side. Once you've matched and mirrored the sides, now you mirror the direction that you're going. I'm not going to choose the 15 because there's no match there. So 18 over x minus 6. Notice the direction, 24 over 8. Cross multiply. 18 times 8 equals 24x minus 6. There's a shortcut here rather than distributing the 24. As I know that pieces of 24 can go into these numbers. So rather than distribute, you can divide it out. I know 6 goes into 18 and 24. 6 goes in there 3 times. 6 goes in there 4 times. 4 goes into 8 twice. So 6, 2 times 3 is 6 equals x minus 6. I add 6 to both sides. And our unknown x is 12. When you plug it in, 12 minus 6 is 6, and then you check the ratio. My ratio is going to be 3 to 1. 18 to 6, 3 to 1. I know I'm correct. Today we're going to talk about similarity shortcuts. Similarity shortcuts. But before we talk about similarity shortcuts, we're going to talk about the congruency shortcuts, because that is what you're familiar with. Congruency shortcuts. If a certain something is minimally true, then the triangles are congruent, which means they have the same shape and the same size. Same shape, same size. That's the definition of congruent. Same shape, same size. And there are 4 shortcuts for congruency. Side, side, side. That gets us congruent triangles. Side, angle, side. That will get us congruent triangles. Angles, side angles, that are known as hamburger. That gets us congruent triangles. And then angle, angle, side. That will get us congruent triangles. What we're going to learn about today is what are the shortcuts for similarity. And we're saying this, if this minimal something is true, then the triangles are similar, not congruent, similar. Basic definition of similarity, same shape, different size. Same shape, different size. The first one is angle, angle, similarity, which says if I have 2 congruent corresponding angles, then the triangles are congruent. Not congruent, similar. Same shape, different size. That's called angle, angle, similarity. Please note that little similarity sign. You must have that. Watch out for parallel lines in triangles. It's very common in this situation. Go ahead and draw those parallel lines now. You have one triangle. You have a second overlapping triangle. They share this reflexive angle, and then I have a set of corresponding angles. This is a very common angle similarity. This triangle in here, smaller one, is similar, same shape, different size as this triangle right there. The second side similarity, which is if I have three equal side ratios. Watch very carefully. Let's say I have a triangle that the side lengths are 2, 3, and 4 inches. The other one is 4, 6, and 8 inches. 4 to 2, that's a 2 to 1 ratio. 6 to 3, 2 to 1 ratio. 8 to 4, 2 to 1 ratio. So notice the side ratios are the same all the way around. I know those triangles are similar by side, side, side similarity. You must have that side, side, side similarity sign. This simple side, side, side means the triangles are congruent, not similar. So be careful you don't use that when making reference to similarity. This one says if I have a pair of equal side ratios, notice my ratios here are 2 to 1, 2 to 1, and then a squeezed angle in the middle. That's side angle side similarity. Let's test these shortcuts on the other side. So let's take a look at these couple triangles here. I have this triangle. I have this triangle here. And I have this triangle here. And if you pull these triangles apart, you can see that they have this angle in common and this angle right here in common, which would make them similar by angle similarity. And you have these triangles, again, they're overlapping. Let's pull these apart this time. Now let's bring our numbers over. In our small triangle, that's 10. And right here, if you take a close look, the whole thing is 24. And from here to here is 9. So 24 minus 9, that's going to get us 15. In a larger triangle, that's 16, and then this is 24. Now, we already know that they share this angle right there. So I have a shared angle. Now let's check the side ratios. 10 to 16. And then 15 to 24. Top 2 goes in there 5 times, 2 goes in there 8 times, 3 goes in here 5 times, 3 goes in here 8 times. So look, my ratio is the same. Check, it's a side ratio and a side ratio. I know this triangle here is congruent by side, angle, side, similarity. This page I want you to do on your own. Pause the video, restart when you're done. Welcome back. Take a look. You had parallel lines here. So instantly that means you have armpits of the Z. A pair of angles. And you have vertical angles. So I know those are similar by angle-angle similarity. This one, I'm going to check my ratio. So I'm going to go short to short. And it's 15 is short, 26 is short. Medium to medium, 21 to medium, 34. And 24 to 40. There is not a single number that's going to reduce 26 to 15. And there is not a single number that's going to reduce 34 to 21. And there is not a single number that's going to reduce 40 to 24. So these folks are not similar. Before we move on, we need to recap our understanding of dimensions. Things that just have length have one dimension. So we express that ratio from x to the first dimension, y to the first dimension. And a common expression of the first dimension, think picket fence. Perimeter, you want to walk your pencil around. Perimeter can be unwrapped, if you will, into a single length. That is why perimeter is only a one-dimensional concept. Then you have area. When you think of area, think of glass. Area is a two-dimensional concept. When we work with the area ratio, the exponent is going to change. X to the second, because I'm in the second dimension, y to the second. Volume is a three-dimensional concept. So if this was an empty box and I filled it with water, that would be volume. Volume is a third-dimensional concept. It's going to be x to the third dimension, y to the third dimension. You will see this as we move forward. But it's super important that this one concept, the exponent of the ratio change when with the dimensions. The exponent of the ratio changes with the dimensions. As the dimensions change, length, area, volume, the ratio that you're working with will change. Say it again. The exponent of the ratios changes with the dimensions. So this will help you understand this. Things that have the same dimension have the same ratio. Say it again. Things that have the same dimension have the same ratio. Let's do a couple problems with you to help you understand this. We write it again. So because things that have the same dimension have the same ratio, and the fact that perimeter is only one dimension, we can do this when we're working with triangles. The ratio of the sides is going to be the same as the ratio of the perimeters. The ratio of the sides is the same as the ratio of the perimeters. Why? Side length is one-dimensional. Perimeter length is also one-dimensional. Things that have the same dimension have the same ratio. Let's try this problem together. The EFG is similar to PQR. EFG is larger than PQR. Side EF is 12, side PQ is 8. The perimeter of EFG is 36. Find the perimeter of PQR. So first we're going to draw triangles, and we need to align these corners because these triangles are similar. This means they have the same shape, different size. EF is larger than PQ. Side EF is 12. Centimeters. PQ is 8. Notice I'm crossing stuff out as I count for it. The perimeter is EFG. I'm walking around. Like a little arrow to represent the perimeter. Is 36. We are looking for the perimeter. Trace it. That is an unknown. Now there's a long way or a short way. The problem is I can't get the perimeter directly here because there's no segments to add up. So we're going to have to get the perimeter in. So what we just was that the ratio of the sides of similar shapes is the same as the ratio of the perimeters. And the reason is they have the same dimension. So we're going to go side over side. 12 over 8, I'm going to work left to right, equals perimeter, 36 over unknown perimeter P. Let's cross multiply. The key to multiplying it, so multiplying the factor. I'm going to factor this out. Bring this 12 over. I know the 12 goes into 36 3 times. 3 times 8, 21. Oh, 24. Excuse me. So my perimeter is going to be 24 PM. I could see that 12 to 8. 4 goes in there 3 times. 4 goes in there 2 times. 36 to 24. 12 goes in there 3 times. 12 goes in there 2 times. Check. I see my side ratios. Perimeter. My perimeter that I was looking for here is 24. Let's change this up just a bit. It said Mr. Thomas and Mr. Lee have obtained the yards of different colors. Mr. Thomas's yard and here is Mr. Lee's yard. They are same shape, different size. The width of Mr. Thomas's yard is 15 feet and the length is 30 feet. The scale factor, the side-to-side ratio of Mr. Thomas's yard is 3 to the scale factor. Find the area of Mr. Lee's yard. Now watch very, very carefully here. Scale factor by definition is 10 dimensions. Come over here in the corner, we're going to make 1D, 2D, 3D. The reason why we're doing this is the exponents of the ratio change with the dimensions. And I notice I have a change in dimension. I have side length 15 and 30, but I'm being asked for the area. Side length is a one-dimensional concept. Area is a two-dimensional concept. So we're going to get our ratios over here. Our first dimensional ratio is 3 to 4. Technically, that's 3 to the first, 4 to the first. Our second dimensional ratio would be 3 squared, 4 squared, which become 9 to 16. And our third dimensional ratio would be 3 cubed, if these became boxes, if you will, to 4 cubed. 3 times 3 times 3. Is 27. 4 times 4 times 4 is 64. So when we talk about finding the area of Mr. Lee's garden, backyard, we're going to be in this second dimension. Why did I keep happening? So the scale factor is 3 to 4. So first I'm going to find the area here of Mr. Thomas's garden. And that's going to be simply 30 times 15. And we get 450 feet squared. So the area of Mr. Thomas's garden, we're going to use the area of Mr. Thomas's garden, the unknown area of here. I'll just use A. But the ratio we're going to use is not 3 to 4, but the second dimensional ratio, which is 9 to 16. And then you cross multiply. I know that 9 will go into 45 5 times, and there's a 0. And so I'm going to do 15 times 16. Let me take a look here. My area that is going to be Mr. Lou's garden is going to be 800 feet square. 800 feet square. And I did that because I can use the second dimensional ratio because the ratios change with the dimensions. Let's try another one. This one I want you to try on your own. Pause the video. Restart when you're done. So EFG and PQR are similar. EFG is larger. We're going to make sure you should have, make sure you aligned your vertices. Doesn't matter where you start. They are similar. Side EF is 15 centimeters. Side P, that should read, no, side EG, I am not reading that correctly. Side EG, that's because I didn't put my finger on the paper like I've been training you guys to do. So even the teacher can make mistakes if you don't put your finger on the paper. Side EG is 15 centimeters, and side PR is 10 centimeters. So that when you're done. The area of PQR, the entire area, is 20 centimeters squared. What is the area here? Now, I haven't even taught you guys how to find the area of triangles yet. It is not area equals length times width. That does not apply here, folks. Be very careful. Area equals length times width is the area of a rectangle. I have not even taught you how to find the area of a triangle. But we can do this a backdoor method using similarities. So, 1-dimension ratio, 2-dimension ratio, 3-dimension. My first dimensional ratio, if I'm going to go side to side, that's 15 to 10, and reduce it. 5 goes in there 3 times, 5 goes in there twice. So my 1-dimensional ratio is 3 to 2. My second dimensional ratio, which would be area to area, would have to be 3 squared to 2 squared, which becomes 9 to 4. If this turned into pyramids and we were filling them with water, our 3-dimensional ratio would be 3 cubed 2 cubed, which would be 27 to 8. We are going to make a proportion. We are told the area of our larger triangle. So I'm going to label small to large. That's important when you're doing proportions. You know which direction you're going. Small to large. The area of our larger triangle is 20 cm squared. We do not know the area of our smaller triangle. That's what we want to know. But the ratio of these have to reduce Alrighty guys, I labeled this wrong. This should have been EFT. And this should have been PQI. If you guys were tracking with me, you immediately know why that's the case. So that 20 should have been the smaller triangle. So we're going to go ahead and flip these. If you wreck your head trying to figure that out on your own, I apologize. Hopefully the fact that you experienced difficulty means that you understood the direction it should have gone with that 4 and the 9. So our small to large ratio is still going to be 4 to 9, but the area, this 20, actually belongs to the smaller triangle, 20 feet squared, and then we're going to find the area of the larger, which is unknown. So 20 over unknown area. We cross multiply, and we get 4 times an unknown area equals 9 times 20. Divide by 4. And the area of our larger is 9 times 5, which is 45. We cm squared. And if you look carefully, you're like, but wait a minute. 20 to 45 is not a 3 to 2 ratio. It doesn't match. You're correct. That 3 to 2 ratio is one-dimensional. But 4 goes into 20 4 times. 5 goes into 20 4 times. And 5 goes into 45 9 times. And that 4 to 9 ratio is what we're looking for because we're in the second dimension.